morning everybody, and let us continue our discussion on the linear drive. In the last class we have seen there are different kinds of linear drives, and we have seen what are the advantages and disadvantages of those linear drives. So, let us continue this topic further. So, in the last class we have seen that there are three different kinds of linear drives. So, the one is the iron core, another is the air core or the ironless, and third one is the slotless. So, if you consider these attributes like a cost, attractive forces, cogging, force per size, thermal characteristic, force or weight and force or strength, then there are different way you can get the idea that which one is better in this case. So, if you consider cost only, then slotless is the lowest cost and air core is the highest cost. Attractive forces, that means the attraction between the magnet and the forcer, then it is highest in this particular case, and this is the moderate. So, if you see all these things, that you will get actually something in between for this slotless compared to this iron force and the iron core and the air cores. Force per unit, it is now say it is more good in this particular case. So, if you are whatever, first you have to decide that which one is your primary objective or the primary attribute. So, depending on that you have to select one motor. Obviously, you have to compromise some of the parameters, because none of this motor is giving all the advantages which is required for a particular application. So, some compromise must be made for selection of these motors. Now, let us discuss all the advantages and disadvantages of this linear drive. So, first one is the high speed, because speed is limited by the wear and friction in that conventional drive here, because we know that here we are not getting any contact between the two surfaces. So, the speed is limited by the bus voltage and the speed of the control electronics. How frequently you are changing those poles between the north and south, depending on you can get the speed here. So, typical speed of the linear motor is 3 meter per second with a 1 micron resolution and over 5 meter per second for the coarser resolution, because we have seen in the earlier that everything depends on the resolution. If you are more high resolution, what is happening, that moving very fast is a problem, because again you have to get the signal processing also such a high rate. So, if your speed is 3 meter per second, you can get within a 1 micron resolution you get, but if you increase the your speed, then what is happening, that similar way you have to actually increase the electronics for the resolution or the encoder also. So, that is very difficult. So, by increasing the speed, then what you have to do, that you have to actually use the coarser resolution. Then you have to actually compromise with thing, instead of a 1 micron you can go with a 5 micron or 10 micron, then you can go with the very high speed. So, that is the one of the way you can compromise with respect to resolution if the primary criteria is the speed. So, it is a maintenance free mostly, because it does not have so many mechanical components, and another thing that there is no contacting parts. So, whatever is the moving parts, those moving parts are separated with each other. So, it does not have any wear. So, that is the way it has some advantages in terms of maintenance. Higher precision is there. So, here everything depends on the feedback devices. The accuracy, resolution and repeatability of a linear motor driven device is controlled by the feedback devices. So, what is the, with a wide range of linear feedback device available, resolution, accuracy are primarily limited by the budget and the control system bandwidth, because we know that we are getting a feedback resolution of linear encoder with a 0.1 micron also. So, but the cost is also very high. So, everything is depends on the what is the budget of your system and what is the control system bandwidth, that how frequently you are getting, how many data you are passing from a 1 second or the 1 unit time. Response is very fast here, because it is give response rate with 100 times more than that of the mechanical transmission. So, that is the advantage here. So, because of that, what is happening, you will get faster acceleration and settling time and no more throughput. So, that means that suppose you are starting one motion, suppose you want to move one component from here to here with a speed of a, consider that 3 meter per second, correct. So, initially it is at the rest, correct. So, from resting position to reach this particular location, you have to spend some time here, correct. So, if you see this particular graph, this is the velocity then it will start and then it will reach to this particular part. So, you consider this is the 3 meter per second, then you have to spend some time here. So, this is called the settling time. Correct. So, if you spend this much settling time, then you have whatever is the second, fraction of second is also sometime is important when you are working with a very high precision and hundreds and thousands of component. So, whatever is this time, you can reduce this time, because now you are getting a faster acceleration. So, right now suppose it is taking this much time, and if you use this motor, and it may take very small time. So, it is reaching this part. So, this is the time you have to spend in settling time. So, that is settling time. So, if it is responding very fast, then your settling time will be very less. Quickly you are reaching to your required velocity, and then you can start performing your operation. So, you are reaching to required position very fast. So, obviously your throughput is very high. Throughput means the production rate, how fast you can process one component. So, that is called throughput. Right? Stiffness, because no mechanical linkage is there. So, it is a matter of the gain and the current. So, how much is the current you are supplying, and depending on that you can get the stiffness of the motor, and it is limited by the motor peak force and the current available and the resolution of the feedback. Because if you want to make it more and more stiff, then what is going to happen, that you have to sacrifice with the resolution, because then your weight will be very high, inertia forces will create a problem at the later stage. Zero backlash is there, because without mechanical transmission component we do not have any backlash here, that we have seen in the air bearing also and the hydrostatic bearing also. Resolution consideration, because motor must be displaced by a one feedback count before it will begin to correct its position, because that we have seen that if your feedback device is a 1 micron, then your motor must be displaced by 1 micron in that particular direction. And we know that there are wide range and size are available. So, depending on your application, you can find out that how much is the distance you want to move, 10 millimeter, 1 millimeter, 100 millimeter. Depending on that, you have a different size, as well as weight also. If you want to keep a 500 gram weight or 1 kg weight, depending on, you have to select a motor. So, there are wide ranges available. So, selection is not a problem with this particular motor type. Only thing is the cost is important, how much precision you require. Based on that, you have to select a linear drive. But since there are systems with a very complex circuitry, there are some disadvantages also associated with the linear drive. So, first thing is the cost. Now, these motors are very costly, and relative volume produced and the price of the magnet, because what we are doing here, that we are using a rare earth magnet, and these magnets also you have to make a very flat, because you have to also make those things precise. So, longer travel motor becomes more expensive, because we have seen that we are putting more magnets to get the longer travel, correct. So, that is the reason that if you are increasing the travel length, then your cost will be increased, because you have to put more number of magnet with a very highly precise dimension, because there are also tolerances with the magnet. If your magnets are not as per the design, then you will not get the complete assembly done within the tolerance limit. Another thing is it is coupled with the linear encoder. So, linear encoders are costlier than the rotary encoder, because what is the thing here, that I will let me discuss those things that location, because rotary encoders are just a disc only. So, whatever is the travel length you are getting, that is the size of the rotary encoder will not change, but if the length is very large, then what you have to do, you have to make the linear encoder also very large. So, and this is the way that your linear encoders are very expensive compared to the rotary encoder. Again, the cost of the linear encoder increases with the travel length. So, if you increase the travel length, two things happen. One is the cost of the magnet increases, and another is the cost of the linear encoder increases. So, cost is a big issue for acceptance of this linear drive for different applications. Higher bandwidth drives and controls are required, because we know that we are moving very fast way, because for moving 3 meter per second, you have to switch over this current very frequently, and that is making very problematic situation when you are working with a fast ration. So, these are the no mechanical reduction between the motor and the load. Servo response bandwidth must be faster. right. So, how fast you are responding to the signal, the way you are changing the switching the power supply, then how much time it required to move these things. So, everything should be very fast, and when you make this thing fast, then heating is also one of the issue. So, this includes the higher encoder bandwidth in the servo update set. So, you have to frequently update the next position whenever it is reaching the part, because if you are moving from one location to another location with 3 meter per second and you are stopping that things instantly at that location, then that servo rate should be updated, that location has been reached to that part. So, now you have to stop that part. So, inertia is also playing important role, how fast you can stop at one location. Force per unit package, that means what is the size of the component, how much is the force you are getting. So, in this case, this is the downside of this particular motor. So, that linear motors are not compact force generator, because if you want to generate a very high force with a small volume, so that is not the right choice for that, compared to the rotary motor with the transmission offering the mechanical advantage. So, if you take this advantage, that suppose you want to create a 65 Newton of a continuous force. So, if you take this force, then how much is the cross section of the motor is required? So, you have a 50 by 40 is the cross section what is required. But if you see the 10 millimeter diameter of a bolt screw, at that time it can generate 400 Newton of thrust. So, if you see this particular thing, then one way we are talking about the force which is very high in case of a bolt screw, and the dimension, if you consider how much is the dimension of the system, then it is a 50 by 40, but here within a 10 millimeter diameter you can get very high. But this is not the criteria of selection of the drive, because what is our objective to select the or use the linear drive is the precision and the friction and wear less component. But this is one of the example that if your primary target is the force, then it is better to go with the other systems. Heating is a issue, because heating is because of the current supply. In most linear motor application, forcer is added to the load. So, any I square R losses are then directly coupled to the load. So, that is the problem here. But many times what happens that we apply some of the thermal management techniques. So, that is mostly the air cooling or water cooling we apply. So, in that case we can actually reduce this heating problem very low level. And another thing that we know that heating is because of the electrical supply only, not because of the mechanical friction and wear. So, that is one of the ways that we can make this thing this particular disadvantage very low, so that you can actually neglect this thing for the other application. No minimal friction, because this is what we required, but sometimes what happens that this is also creating a problem, because you have to have little bit of friction. So, let us see that this may not sound like a problem, but it has a problem. Now, consider a situation, the linear motor is traveling with 3 meter per second and it loses power. Now, what is happening here, because if you do not have a minimal friction, then what is going to happen, that this particular whatever motor is moving, it will directly go to the end position without wasting too much time. That means, it will not take so much of time to reach to the end position. So, it will strike to that location and then there may be some mechanical damage or some other problem. So, this is actually our requirement, but sometimes when you are not you do not have a power backup or some other electrical connection, then what is going to happen, that where in a sudden power failure or something happens, at that time controlling of this particular system is a problem. So, you have to have some type of stopper, or so that even if there is a power supply, you have a power backup. So, you can smoothly reach to the one location, or you put some stopper, so that it will not directly strike to the end position or the limit switches. So, those are the disadvantages of the linear drive. So, now coming to the feedback encoders. So, till now whatever we were discussing, every time we have seen that feedback controller or the feedback encoders are playing important role. Whatever is the resolution of the feedback controller, you will get the step size of that much only, not because of the system which we are using. That we have seen that if you have a linear drive with a 0.1 micron of resolution, but your feedback drive has a 1 micron resolution, then your system will work with a 1 micron only. So, let us discuss about the feedback controllers, what are the feedback encoders available. So, how small a part you can successfully machine depends greatly on the drive and the motion technology built onto your machine, micro machine. Right. So, there are position feedback. So, position feedback means it there we have two position, one is the linear position, one is the rotary position, correct. So, in that way we have two encoders, one is called rotary encoders, which will measure the rotary position or the rotational direction of that. Other than rotary direction, you can also get the linear position by the rotary encoder, we will see that thing. Another thing is the linear encoder. So, for position bit back we will look about, because if you are looking with a spindle RPM, then you have to put a rotary encoder into the spindle, and if you are talking about the x, y and z linear motion, then either you use a rotary encoder or you can use the linear encoder. So, these are the two things, and other than two there are two different types also. If you are talking rotary encoders, it has two types, incremental encoder and the absolute encoder, and similarly for the same way for the linear encoder also. So, total we have 4 different type of encoders. One is the incremental rotary encoder, absolute rotary encoder, incremental linear encoder and the absolute linear encoder. So, let us see those things, that how these things are playing important role. So, first thing is the rotary encoder, incremental rotary encoder. So, this is the diagram of that part. So, what is this thing? That it is an electromechanical device which convert angular motion to a analog value or the digital code. So, right now we are talking about this particular incremental. So, how this thing is making sense? So, it has, this is the motor shaft, correct. On the motor shaft we have attached one rotor plate. So, what is this rotor plate? If you see this rotor plate says some marking here. So, this whatever is the black color, these are opaque, and whatever this white color is, that there is spacing in this, white color are the transparent, correct. And now what is happening here? So, this is what we are talking about, this outer periphery, correct. So, we have a light emission diode. So, light will pass through this thing. It has a 3 light source, and similar to that we have a slit A, slit B and the slit Z, correct. So, when light is passing through this thing, now consider this situation that we have a, these are this part and these are the, consider the opaque and the transparent region. Correct. So, light is passing through this part. So, when it is rotating, if these particular transparent parts come, then light will pass through it, and on the other side there is a phototransistor available. So, whatever is this, these things are aligned with each other. So, this one light is aligned with one phototransistor, another is similar to like that. So, whenever there is a transparent part, light will pass through it and it will get a signal. Whenever light will strike to this opaque region, black portion, light will not pass through it, your phototransistor will not get any signal. So, this is the how. So, if you rotate a very faster rate, faster way you will get this particular signals, right. So, that is for the slit A and slit B. Why we are using slit A and slit B? Let us see this diagram, right. So, this is the signal. Now, this is what we are talking, right. So, this is the signal of the A. So, whatever you are thinking of, so let us write here A, B and Z. So, this is A, when it is passing through it, you will get one signal of A. So, this one particular pulse belong to the one time the light is passing through and your phototransistor is getting a signal out of it, correct. And similar way you are getting a B. So, this is the B signal and this is called the Z signal. So, what is this Z signal? Because now if you see this A and B are actually lying on this particular black and white spoke kind of thing, but here if you see the Z is here. So, Z is actually the reference position. Correct. So, reference position is only one here, consider. So, now that is because that if you are rotating this particular encoder and suddenly there is a power failure or something, and then your position is somewhere here, correct. So, at that time this particular incremental encoder will not be able to find where is the position. So, it will rotate it, and again when this particular Z will reach to this location, then it will get the signal that this is the reference position, and then it will start counting the position. So, that is about that part. So, what it will do, that it will actually do a travel distance and the direction information. Now, consider that how do you know that it is rotating in clockwise direction or anti-clockwise direction, correct? So, let us see that thing. Now, that is done by the slit A and B. Now, you can see that this A and B are actually side by side, not the one after another. That means, not back to back, but it is side by side. So, now consider that it is rotating in the clockwise direction, right. So, if it is rotating clockwise direction, when it is rotating, your A slit will get signal first, because it is located first. So, this is the signal strength of the A. So, it is starting with this particular leg. So, how much is this particular leg between the signal A and B? That is the distance between this particular A and B, correct. So, this is the A signal, and after certain time you will get the B signal, correct. So, our sequence is from A to B. So, it is rotating in the clockwise direction. If you rotate in anti-clockwise direction, what is going to happen? That you will get this signal as a B and this signal is A, because now B will get the first signal and then it will get the A signal. So, not only the rotation, but you also will get the information about the direction, that it is rotating in clockwise direction or anti-clockwise direction. That is about the rotational motion. Now, how do we convert this rotational motion in terms of a linear motion, correct? Because these rotary encoders are also used for measurement of a linear motion. Because now consider this is the shaft, and shaft has a lead screw, correct. So, lead screw has a pitch, correct. So, now first we have to find that what is the amount of rotation. If it is a 360, because we know the what is the pitch, that if you rotate one shaft with a 360 degree or one rotation, how much is the translation motion, correct. So, that is pitch. So, if you are rotating one full rotation, we know the what is the pitch of the lead screw. Suppose it is a 5 millimeter, 5 mm of the pitch of this lead screw, then what is going to happen, that for one rotation you may move the 5 millimeter in the translation motion. But if you move just a 1 degree or 2 degree, then what you have to do, you have to divide 5 divided by 360 degree. So, that you will get a one again motion in that particular direction. So, whatever is the motion you are getting, you have to actually back calculate with a calculation of the rotation and the pitch screw, and whatever count you are getting, that count you have to find that counts the number of output pulses. So, whatever is the pulse, one pulse equal to the distance between these two things, that how much is the spacing between this black color and white color. Smaller the spacing, higher is the resolution, correct. So, this is the spacing. So, how you can define the smaller the spacing? Higher is the resolution, correct. So, that depends on what is the spacing, which is 1 micron, then you will get the signal within a 1 micron. If it is a 0.1 micron, you will get a signal with a 0.1 micron. So, that is how you can make it. Right, but problem, what is problem with this thing, that it cannot tell you about the absolute position, that we have seen in the earlier class, in this earlier slide, that suppose it is reaching here some location, suppose it is here, then what is happening here, that it has to move to this z location here first to get that what is that position, because unless it will reach to that reference position, it will not tell you that what is the part. So, what is the location of this? So, what is that thing, the machine needs to be reference or the home. So, this z is called the home position or the reference position. So, that is one problem here with this particular incremental kind of thing. Okay. So, it provides output only when the shaft of the encoder is rotated. It is obviously correct, because if your shaft is not rotating, you will not get the output. So, a reference position can be anywhere, is reset. So, this suppose it is here, then it will be reset, and pulse count from that position is detected, the amount of rotation. So, this particular thing will be reset, that means this particular location will go to that location and then it will get the signal. So, pulse count will start getting position once it detect this particular Z part. Right. Second one is now the absolute. So, the earlier case was the rotary kind of thing. So, what is the advantage? Earlier disadvantage was it was not able to find the exact position, that means instantaneous position, but now this one is called absolute. So, output is in the form of a this was, so it is able to get this thing done. So, now how is the difference than earlier case? That earlier case it was the lot of different type of slits and it was getting a signal, but here now what is happening here, that you have a series of LEDs and on the other side you have a photo transistor on the part. So, now here what is happening, that it is creating one type of code here. In earlier case we are getting one signal here, but here it is getting a code and that code is actually unique for each and every instant of the rotation. So, when you are rotating this part, so this black color and this white color part, everywhere it will generate one signal and whatever is the final output of this all the signals, you will get a binary code and that binary code belongs to the one particular location of the signal. Right. So, it consists of a glass or plastic disc with a opaque and transparent area. So, these are the opaque and transparent area. In earlier case this was available, this outer periphery whatever is this lines are available, but this is working on a different principle. So, light source and the area of photo detector reading the optical pattern. So, here you are getting one optical pattern. Earlier case we were getting one 2 or depending on 1 or 2, that is called A slit and B slit and Z slit, you are getting some waveform here. Here also you are getting waveform, but these are the unique for a one particular instant, but in the earlier case you were getting the same thing. So, that was the difference. It produces a unique binary code output for each distinct angle of the shaft. So, what is the advantage? The shaft position is always not even after power failure, right, because now once it is rotating, what is happening here, that if this is the one particular situation, that this is the particular location through which it is passing the light. So, if that is the case, then what is happening, that wherever you are not getting any signal, so those particular things are actually 0 and you are getting signal from few location only. So, for each and every location you are getting a unique system, that means there is a distinct angle or unique binary code. If binary code is unique, then you will never miss that position. So, as soon as light is switch on again after failure, then your shaft or that encoder will tell you the where is your position exactly here. But that was not the possible in earlier case, because in that case if that Z was here, then you have to move to that location and then it will start the counting of the linear motion or the rotary motion. So, there was a lag if you are talking about the incremental encoder, but this is the instantaneous motion detector, that is called absolute encoder. So, let me finish this class here. We will continue discussion about rotary encoder and the linear encoder as well as for some other purpose in the next class. Thank you very much.